So it is my great pleasure to introduce Dr. Rebekka Burkholz, who will be giving a talk about smart and sparse. Now, Rebekka, no matter how happy we are that she's here, in a way, it's a little miracle, because she never really formally applied for a tenure track position the regular way. That's okay. I promised myself to keep this introduction short, right? So however that happened, right? So whatever the reason that she's here, you can ask her afterwards. Now, I have one question for all of you. One question, one remark. Especially those of you who have been in the tenure track selection procedure yourself, who have given an application talk. Well, maybe you do not know Rebekka's work so well, but you do know what she does when you give a talk. She asks question after question after question. So all of you, during this talk, think of questions and ask them afterwards. So, Rebekka, please tell us everything about sparse and smart and efficient and green. We're very much looking forward to your talk. Please take it away.
Thank you. Thank you. Well, thank you so much, Gilles, for this very kind and also funny introduction. Just in case you wonder, Gilles had a big hand in me coming to CISPA, so thank you very much. It's such a big pleasure to be here. Thank you all for coming. It means a lot. And I hope you're a bit curious about, can I actually use that? Let me see. Yes, I can. Okay, you're hopefully curious about what I mean with all of this green and efficiency, and it's kind of a bit curious potentially that everything looks blue. And the reason for that is that the basis of what I'm going to talk about are so-called cascade processes. And you can think of them, as a waterfall, for instance, or like glasses that contain some water. And at some point they overflow, and then this water cascades through the different kind of levels and through the different glasses. And the question is, but before we go into big depths of this one, we had great precedents of that before. So I was asked to talk a bit about how it all started and how, I ended up here. And how it really started with, where the water even came from was on the April 26th in 1987 in Frankfurt in Maine. Was born to these two wonderful people over there, my parents, Albrecht and Elke. And, what I should maybe say about this is that, the question is, is that kind of a great predictive story, of something, what is happening? Just a year earlier, there was this big accident, in Chernobyl, which was a nuclear disaster that was quite worrisome. So you could think of that, maybe, 1 year, the question is how you interpret that, maybe 1 year later, we needed to come to balance that out, or, this is a predictor of what happens in the future. I was given the name Rebekka, and my parents had a very clear idea of what it was, which of the two, of course. So I was given the name Rebekka, which is Hebrew and means to bind, connect, or maybe even secure and capture. So what a coincidence that nowadays I'm leading the relational machine learning lab, as if they had known. And then, afterwards I had a wonderful childhood. The animations are not working. Let's see. Not very well, sorry about this. So I had a wonderful childhood that, I loved school, and, I received all these kind of resources that were really helpful then later on, and to develop this curiosity for this question, what did I want to study? And it was, of course, I was always bad in making decisions, so I couldn't really decide whether it should be math or physics. I loved both, so I studied both. And yes, and then I went, for some time to Sweden, and I'm really grateful also for a scholarship that I received during that time. These were really formative years because, it was really interesting to look into different fields and to just, I didn't have to worry about how could I use it. I knew I was on a good track, and I could just enjoy learning. So that was a pretty nice time. But I had always had this pressing question, what should I do? Should I do math? Should I do physics? What should I do afterwards? Because I knew I wanted to become a researcher. And and that was decided then at some point later. And that is, so I went to ETH Zurich and did a PhD in something very interdisciplinary because, for someone who cannot make decisions and wants to connect different fields, that's exactly the right way to go. and they worked on complex networks, specifically on these cascade processes with Frank Schweitzer, my doctoral father. And I also won an award, these kind of things you do then during this time. And yes, and that kind of gave me more resources to, to continue on this journey when you wonder most likely where all of this AI and computer science is coming next. Not yet. So during this PhD in complex network science, though, it was laying the groundwork for what I'm going to talk about today. And these are these so-called cascade processes. And you could think, though, it was in a different kind of application domain. So think of that, for instance, as a social network. So people are connected, my name relates these kind of people. And you could study, for instance, epidemic spreading on this process. Unfortunately, nowadays, everyone knows what that is, right? Think of COVID or something like this, a pandemic going on. So people infect each other via this contact network. And this is how this continues. But you could also, use very similar models to model something like information propagation through online social media, maybe even fake news and how they propagate through these networks. And you can study opinion formation. And maybe keep that in mind because we'll come back to that opinion formation. Because as it turns out, opinion formation is also something that can happen in agentic networks. Okay, you could also think, of course, of cybersecurity. I didn't have that at mind at the time, but you could also think of cybersecurity risks, right? There you could have power outages. We did look a bit into, for instance, power plants and what happens if something bad goes on, how does this cascade through a power grid. But also some kind of cyber incidents and attacks on solar winds or something in this direction. And I think also for a fact that I think Christian Rosse also used even some similar kind of models to identify the source of some of these cascades, so of a cyber attack. So, there are opportunities to use these kind of models also in this context. But I studied economics, I'm afraid. So most of the work that I did was quite theoretical, but it was motivated by this financial crisis in 2008, 2009, and potential financial contagion that would propagate through banks that trade with each other, and they have exposures to each other. And if a bank fails, and it was maybe too big to fail, it could also drag other banks down because of the exposure to it. Yes, and you can also, so really the topic of that was close to my heart and that I came up with was to study systemic risk in trade networks. And we are still working now, on these kind of, we just had a meeting today about trade, international trade and food trade, and this question like, how are countries exposed potentially to risks that happen in other countries, and how is their food security dependent on it? That also won an award, but yeah. Okay, and yes, but you could also study that on a very theoretical level in the context of complex networks, for instance. And that was an epiphany that I had at the end of my PhD. You could also study that in the context of machine learning. So specifically deep neural networks, graph neural networks, or graphical models. And what I found most striking at the end of my PhD is that these specific type of cascade models that I studied, so I studied different kind of classes, but the specific one that is unfortunately the most difficult one to tackle, but that I could make analytically tractable, so-called fiber bundle models, they have a one-to-one correspondence to deep neural networks that are equipped with ReLU activation functions. So you could also interpret that, the evaluation of a neural network. So basically you take this large-scale machine learning model and how it produces an output, you could understand as a cascade process, because we cascade now through this kind of neural network. And I thought this is so interesting, and and of course I thought like maybe I can use these kind of theoretical derivations that I did to make deep learning more efficient. So I did a postdoc in this area. And some of you might feel reminded of a talk that I gave almost to everyone in preparation of an ERC grant interview. And that set the groundwork for something that I would do much later, because as it turns out, once you do a postdoc, PIs do have an idea of, what kind of projects you should work on. So, and I did some really interesting work at that time at the Machine Learning Institute. So that's when I switched to computer science. And, but I worked also in collaboration with cardiologists and brought in this kind of medical component into it. We also got a grant in this area. So that was a very formative time also because I learned to write grants, and that became quite important also later. Well, and during that time, that was for the first time roughly, that I really entered machine learning, and I wrote my first paper exploiting this one-to-one correspondence between these deep neural networks and cascade processes. And I developed an algorithms that would make the optimization of these deep neural networks better, because we could design an initialization so that they become better trainable. And that was the first time I went to a machine learning conference, which was a pretty big of a shock because it was huge. And it was absolutely huge. So there are 10,000s of people, something at an event like that. So it was very different from what I was used to. But it was quite an exciting journey. And it was also, look at this, it was 2019. So 1 year later, that wouldn't have been possible anymore because of COVID. So it was last opportunity to do this for a while. And then I continued with, so then I thought now I'm doing quite different things though. So I also wanted to connect better this complex network science view and this kind of biometric application. So I went for a postdoc to Harvard, working with John Quackenbush. And so we also had applications in computational biology, and we could study cancer progression. And that is also what we did. So there was another kind of, there was basically another kind of lawyer to fill. Unfortunately, I should have checked that better. The animations didn't show that well, but we would have now had another kind of level of the cascade. We have fulfilled to collect the resources that are required to do the research that I'm doing today. So, but we used now this view also, this cascade was this view to model now different kind of processes, and this is cancer progression. Specifically, for instance, the accumulation of mutations during cancer progression. So as you see, these cascade processes have really many different kind of applications. And of course, we also studied a few different kind of related problems. And that also allowed us then to take, so I learned much more about biology. It was a really interesting time. And we used then this kind of domain knowledge that we acquired to develop so-called hybrid models. So we could design now neural network architectures that would not look like a neural network, that is more inspired by neuroscience, even though, that's a bit of a stretch also. But that was designed in this context. So we designed architectures so they're specifically good to model gene regulatory systems and gene regulatory dynamics. And that meant, for the first time, that we could scale up these models to the full human genome, so 30,000 of genes roughly. We could make this much more resource efficient and also interpretable, because it would relate now to the theory and the mechanistic insights that the people had already in that time. So it was a really nice, I really liked working this way, because it would combine now also a bit this physics, biology thinking with this, new and exciting field I was getting into, which is called machine learning. Yeah, and the source of it all, now that I'm faculty at CISPA, we're finally, all the resources here have come together. And of course, I'm continue to learn on this exciting journey. But now we are ready, to fund a group, basically to kickstart a group. And at the beginning, the relation between machine learning lab was a bit smaller, and we are increasing over time with many new people. And I got an ERC starting grant, and that was exactly built on this idea to use this one-to-one correspondence between these cascade processes and deep neural networks, and to use these kind of statistical physics view in the end on it to make these models more efficient. So it took quite some time to get there, but eventually, this idea prevailed. So, the whole reason why I changed fields in the end was justified, hopefully. And and now I'm here since 2025. So last year, I got tenure. Thank you all to be with me on this exciting journey and for helping along the way. But don't worry, I'll thank you also properly at the end. Now, I'm afraid I will tell you a bit more about what we're doing currently at this time. So for everyone, because also my parents are here, even though I think they're experts, the greatest experts on what I'm doing. Just to explain the very basic setup though, just imagine we have data, and we want to train now a model. In this case, in most cases, not exclusively, but in most cases that we study, we use neural networks. These are these huge scale things, basically cascade processes. I explained to you already how they work. And then these trained models, where we have set all the parameters and how the water should be distributed, essentially, that helps us then to solve an AI task, and that we can use later. Maybe we also want to, continue learning this, so this is not always that separated. But the big problem here in this case is that this is not a small network, but these are gigantic networks, these models, and we also need really huge amounts of data to make this work really well. And that's where we come in. The problem is, of course, the question is, why would we need these huge scale models? I mean, a lot of data, you might be able, you can think, it sounds intuitive, we need a lot of information, right, to solve a problem. So it's good to see many examples, but why so huge models for that? And as what you can see is, interestingly, even if you fix the data size, if you increase the model size, which you see here, the performance of these models increases. In fact, they are highly over-parameterized, and that seems to lead to much higher generalization performance. So that means they will work much better in practice, even on data that they haven't seen so far. And the question is, of course, why is that? One of the big research questions that we have, and I will tell you in a moment a few of the hypotheses that we have regarding that. But first and foremost, let me tell you why that is a problem. Because you might think yeah, okay, sure, we want to be more efficient, but just consider the scale of the problem first. So think of something like GPT-5 that consists of trillions of parameters, and even DeepSeek, this is the Chinese version that is more efficient, consists of billions. This means that we have really tremendous development costs that normal labs cannot afford. So these are huge IT companies that invest heavily in specialized compute or GPU, and they need an infrastructure that requires a lot of CO2 to just train such a model once. So that costs more than an ERC grant to train a model just once. And usually you don't train just once because you don't get it right the first time. Okay, and even if once you have that model, the operating costs of these models are also significant and not to be underestimated. This is actually the real problem of the IT companies right now, because they don't make money currently with offering us, for instance, something like ChatGPT. Even though they get a lot of reputation for it, the business model isn't really working yet, because it's so expensive to run these kind of models. Luckily, when it comes to the second part, we do have a few options to deal with them, and they are also making these more efficient as we speak. Luckily, as I said, right, we don't need these huge scale models to actually solve the problem. We have many more parameters than we actually need. So this means there exist smaller scale models, and there are even a subset of these larger scale models that can solve the problem, at the same performance level as the original one. And we have contributed to establishing that insight and dealing with it. Oh, sorry. This was a lot. Apologies. Was a bit nervous, and then, you press harder. Okay. So the question is now, how do we get these small-scale models? And there are different kind of techniques, that have been developed, and we are also still developing techniques that work better, that take these huge-scale models and then sparsify them and make them smaller, so compress them. The only problem is with this is that these compression ratios, they might look impressive. We can, maybe, boil them down to a size of 1% or to 10% of the original model size. However, consider, the size that we started with. And it's also not that easy to really use then, if you have an unstructured sparsity pattern, to really, gain speed ups on common hardware that we currently have. So you might need specialized hardware to realize these gains also in terms of compute. So that's one problem. And the other one is we need this, the big model to start with. So, someone needs to invest these gigantic, these crazy amount of resources to start with to even, to make progress, so that we can make them smaller overall. So of course, inference, so we distinguish two times here. The one is training, or the basically building the model, and the other one is inference. So that is when we use a model on a daily basis. And since if you use these models a lot on a daily basis, it's still okay. This is the kind of, in some sense, even the more important part. But if we want to democratize AI and make sure that everyone can, participate in this, then we actually also need to solve the first problem, and that is, instead of using this typical procedure here, that we train a large-scale model first and then sparsify it, we need to get rid of this intermediary step and find a way to train these models from the start and from scratch. So we need to also reduce the development costs if we really want everyone to be involved in that. And I do believe that we do need as many people as possible to be involved in creating AI, because it really changes the way, our everyday basis. You have experienced that most likely already when you use large language models. So that changes the way this has a lot of potential, but the more people are involved in that, the more people, can think of, can make sure that this serves all of us and not just a small part of people that people think of in their demands. Okay, so that's our main objective, and that's also the main objective of my ERC starting grant. But unfortunately, we face major challenges on this way. The first one is we need to understand how should this small scale model even look like. So if we want to be very efficient, very likely we need to know a lot about the problem that we have to design it in such a way that it is able to solve the problem in the end. That's number one, this one problem. Currently, honestly, our algorithms, I believe, but this is now a hypothesis, that currently we can also get away with random models, more or less, and we don't need, at the current level where we can do inference, we likely can also get away with randomness, and we don't have learned a lot of specialized structure. But this is but still, if you really want to bring this down, we likely need to know something about the problem in the design. The even bigger challenge is, though, that even if once we have given that model, how do we train it? It's at the core an optimization problem in the end. So the problem is exactly that these optimization problems that we have, they seem to require us learning much more over-parameterized models because they help us with the optimization. So that we have a chance to find the right and the good parameters of this model. For that one, it looks like we need these over-parameterized models to have a chance, so just finding a solution, essentially, because this is very difficult to learn these complex functions. And these are very nonlinear, complex problems, and it seems much easier to achieve that with the current very simple optimizers that we're using, that we can also scale up to that size. It seems to be necessary that we train, that we have these large-scale models and then do, then compress them, rather than training them directly, because training them directly is hard. So why is that? And we made some progress in this direction. And we have in general, let me first explain you, our general strategy to do this. So our objective is, we want to be more resource efficient on the training side and on the inference side. And that means we want to reduce memory, compute, energy. We want to speed up the development and maybe also the inference. We also want to get this at inference, right? Energy, the inference efficiency. And also, ideally, we want to be able to learn from, to be good in extracting information from small data sets. This is particularly important in the biomedical domain that I care a lot about, because often data there is very expensive to acquire. It's often noisy. We don't have perfect control about the experimental setups. That's why there's a lot of noise in it, and we need to deal with fewer samples. So somehow we need to become very, very good in extracting information from these kind of data sets, and likely that requires a lot more hypothesis and information about the problem that we're considering. So there's some physics thinking going in there, I would argue. Okay, and how can we approach these things? One problem that I'm very excited about and that I will talk about in the end are agentic networks. So this is not only that we have one problem, but we only have one model, we have multiple models that interact with each other. You can imagine, I like complex networks, so of course we're going to do this. But you could also wonder, how is that helping us? Instead of having now this one agentic model, now having multiple of them, how is that even helping us? But this can also help us with efficiency, potentially, because now these models can be more specialized and we can make the interaction much more, basically the collaboration. We can use the fact that they collaborate to find setups that are more efficient. That's one motivating problem in question. The other one, so this is a specific kind of architecture design if you want so, but we can also in general think more about how should these problems, so if we have concrete problems, how can we integrate different forms of knowledge that we have already and different kinds of hypotheses to design architectures that are better trainable, like we did, for instance, for these gene regulatory dynamics. And the third level is actually the optimization. So we need to get better in training these neural networks. But what we are looking into is quite specialized way, is basically looking for optimization algorithms that work good for optimization of deep neural networks specifically. Not necessarily in general, but in the context of deep learning. But let me first start with the first two, because I hope you're still curious about the question why we need these over-parameterized models. And the truth is, we don't know for sure, but we have some hypotheses and some ideas of what's going on. So our main question is, what makes sparse training from scratch so hard? And how is the overparameterization helping us if we train on the overparameterized regime? And for that one, we have, so, I just give you, don't worry, I don't show you a lot of math. I just give you, just an idea of how we like to work. So we do then we study some kind of simplified, very simple problems. This is, the most trivial thing you can think of. That's a single neuron here. So we're looking at the single neuron case, and we train the single neuron and wonder what can go wrong if we train the single neuron. And how is that related potentially to the initialization? Because all of that and the optimization itself. And if we use now a typical kind of optimization algorithm, we can look now here at different cases. So what you can see here, these are the relevant parameters, the A and the W here that we need to train. And there's only one case in the initialization in which when we train this whole thing from scratch, so a sparse model from scratch, and so we know the right model, we know the right structure, we just don't know the parameters yet, there's only one case in which this will work. If we, however, train something that's larger scale, so that has more inputs than we actually need, interestingly, we can get another case. So it works in another case. But as you can also see, we don't get all cases. So what's the reason for that? And we also get actually a mechanistic insight what's the reason for it, because for this, so we have this kind of small scale setting because this is analytically tractable. We can write down the whole training dynamics, we have that all under control, and we can study it and get an intuition what's going wrong. And we got an intuition what's going wrong, and then test it in a large scale setting. So then we train these large neural networks. Big thanks to the CISPA computing cluster, I must say, that allows us to do this kind of stuff because it is larger scale. And we test our hypothesis. And this hypothesis is specifically is, and you might have seen that already in how that was presented, is what seems to be very, very difficult for these models is to learn signs of the parameters correctly. So whether it's plus or minus. It's very difficult to transition through 0. And 0 is very important to us because ideally we want to set a lot of parameters to 0 because then we remove them, essentially. And we do have a tendency, we want to remove them, but they have a very hard time if we still need them, if they have the wrong sign, which they very likely have initially because we don't know what they should be, right, initially. They have a very hard sign transitioning to 0. But if we know the signs, so you don't, I'm showing you tables, don't worry too much about it. I'm showing you tables because, this is what we like to do. I think a machine learning talk probably needs to have a table. But, where we also show that we are better somehow, even though that is not that table. But this one here saying us, tell us is that if we know the right signs and we train the rest, so the magnitude of the parameters, everything works out nicely. Even if we have a sparse mask, but we can train it, we can even achieve a slightly higher performance than expensive sparsification approaches. However, if we initialize that randomly, we lose a lot of performance. That's what this is saying. But knowing the signs is enough. And knowing that now, of course, we can design better optimizers that get better in sign flipping, because there's, of course, also a reason why we have a difficulty switching signs, and that is an implicit bias for sparsity. So we do try to send these parameters to 0 in a way, automatically. We don't have that much under control, though, but that makes it very difficult for them to escape 0 again. So what we did is, we have two kind of different optimization approaches. One uses really overparameterization, and the other one, I know it looks complicated, but it really isn't. We just have, one optimizer step that we extend by an exponential update. And that made a huge difference in how we optimize. And in this kind of setting, so when we design now the implicit bias of the optimizer, we can, in theory, now get all cases. So in our toy setting, we solve our toy setting with this optimizer. That, of course, doesn't mean that we don't have other problems in these deep neural networks, so they consist of more than one neuron, right? So this is not the end of the story, but it does lead to much better performance than what we used to, what we thought. So it boosts the performance even of dense training, and I was really quite happy about this because, no, I haven't done, okay, I've decided I don't show you the table where we are better, so, okay. But what is very exciting about this is that we can achieve a performance now, so it's very difficult on these deep neural networks to consistently improve performance compared to where millions probably of students, have, tune parameters manually and try to improve, performance on these benchmark sets. And we would get a relatively high performance increase just with this kind of model. And it's even orthogonal to another kind of form. So only for the machine learners, which might be interesting, is it is orthogonal to SAM. So we can complement SAM with it and then boost even more performance over SAM. And it achieves a similar amount of performance increase as SAM. And that is very unusual. So we were really very proud of those results. And I will thank the authors also, the joint authors, on this. But this was, the result of a couple of works, that helped us to understand what is actually going on in this context. And we are not done yet. Yes, so I talked a lot about this inference efficiency and resource efficiency. Let me also talk a bit about sample efficiency. That is a different kind of approach that we can take. And that is also quite a modern approach to deep learning now. So currently, you do probably, that sounds like madness, I'm aware of it. If you're not on that field, that probably sounds like madness to you, and we will also resolve some of that for a bit. But what people now think is a good idea, and it does work, is you take now these large-scale models here, you train them on this huge amount of data sets, and now that we have them, we think like everything is okay. And now we use these models, and we just train them a little bit, so we fine-tune them, it's called, on different kind of tasks where we have smaller amounts of data. So we have this kind of huge general model, it's called the foundation model, and we use that now and just fine-tune that a bit to specialize it to different kind of tasks, so we can reuse it. But of course, at the end, we have now this huge scale model, but at least we don't need that much data anymore, because we have learned, you can think of that like, in language. For instance, you have a language model, and that has learned in general how language works, and maybe can speak English or something, or maybe write English, right? Write English. And now you want to, learn something specific about a biomedical textbook or so. And then you specialize it to this biomedical textbook. But it doesn't need that much to read, all books about this biomedical topic, because it has learned already how English works, roughly. That's why people do this. And so a big question now in this context is how can we also bring the costs of this down, and which parameters are the ones that are actually changing, we call this as plastic, and which ones are important to keep or to avoid catastrophic forgetting. So basically what we want is, we want to adapt this model but not forget everything about what it has learned so far while we'll adapt it, which seems to be a good idea because we believe that what it has learned so far should help us. And what was quite striking is, the core observation is in these typical large language models that have a specific kind of structure, is that the parameters that do want to change, that change a lot because I have large gradients here, and Chow, is here the first author on this, he found that these small weights now, specifically the small weights are the ones that want to change. And the small weights is kind of weird because you think like these are the unimportant ones, right? These are the ones, but they, and you might want to change them because, they are not unimportant, so they won't mess up too much of what the model has learned already. But what's interesting is that these are also the ones that want to change, and where there is most gain, if you want so. And we also have some explanations now why this might be the case, and that's specifically related to the architectures that we have. But we could, of course, also exploit that now to only use these small weights, and we know them a priori, and it's very simple and efficient to find them, and only tune a small set of small weights. And that would even improve the performance overall of this fine-tuning approach. And we would also need fewer samples. And we get faster conversion. So that was a very simple kind of idea. But now, for the first time, so that is, these are the core research interests that we have, and we will continue working on those, of course. But now I would like to, basically close the circle and come back to the problems that I've worked on very previously at the beginning when I was talking about systemic risk and cascade processes. And not only, in the context that we study deep neural networks, but I actually want to, use now our insights in the context of something that many people are hopefully excited about right now, and these are agentic networks. And agentic networks is networks that currently is basically the talk of industry, if you want so, because they build now all of these kind of agents and agentic tasks, and what you can see is they predict then that this will be a much bigger also concern for industry in the coming years. But of course these are predictions. Never trust necessarily a machine learning model, but this is what people expect right now to happen. And of course these they start now also not only having one agent now that this works, but they want to have multiple agents now. They build multi-agent system, they collaborate, maybe even compete, but they can work with each other. So think of your, maybe, you know, having an avatar, now you send that avatar, you know, to do all your, I don't know, your administrative, which is, you know, to interact with other people, maybe also to make appointments or something like this. So this is what these agents are supposed to do in future. Oha, that's not good. Sorry about this. This was on my machine that was there, and it is also there. It's just not very visible on that beamer. So okay, think of nodes here, and they look like robots. Okay, okay, interesting. But you can still see, you know, I mean, as a complex network scientist anyways, the connections are much more important than the actual nodes, right? So, well, you can hopefully imagine this. So we have now here, think of this like a fully connected graph, it's called. So everyone can interact with everyone. And this is a typical star-shaped structure. These are very typical setups. So either, you know, you do it very distributed and, you know, everyone can interact with everyone, or you have something like an orchestrator, so in the middle, who's organizing the whole thing. So these are very typical setups. And usually these nodes here would be LLMs now, but there can also be other kind of agents. And what is now we face really some novel challenges in the context, and now finally the time is ripe for systemic risk in these contexts, because you know, we have intelligence now that is distributed, interactive, and you know, basically interacts via a graph structure, and that means that there are all kinds of network effects that are, you know, introduced by this. And these are, you know, we have now the emergence of collective intelligence potentially, so the system might behave very differently than what you would believe or predict based on the single agent capabilities, because there's something, you know, bigger emerging from this. I don't think we all know that from CISPA, right? We are greater than the sum of our parts. We have feedback loops, coordination, delegation problems that are coming in, competition, polarization, herding. All of these are kind of effects that we expect now in these kind of more social, you know, agentic systems. And of course, also systemic risk can emerge in these systems, which means, like, you know, we care about cascading processes that run through this, that endanger the robustness of the system. We might have error propagation forms that are difficult to predict. We have the spread of misinformation potentially, maybe even an adversarial takeover. And we are at CISPA, so at least I should have a talk that is related to some form of risk, you know, this talk. And what I found super surprising, and I'm really excited about this, is very recent work, also with Leah, and her students. And well, we were all really excited to see that a very simple model, an opinion formation model that comes from social science that we used for this opinion formation that I was talking about very much at the beginning, fits this really well, these kind of agentic interactions. And we have very different, you know, these are very complex models that in the end do in a very, very simple things, and that we can model with an extremely simple dynamic model that consists of something like a graph. We have something like innate beliefs. So, you know, they have a belief, for instance, in which answer to a question is correct. And they have also dynamic beliefs that they change over time because of an interaction. And they also trust each other or not. And this is now basically modeled by this graph via which they interact. And then they update the beliefs in multiple negotiation rounds, if you want, so, or deliberation rounds. And basically they have a form of stubbornness that, so to which degree do they, you know, stick to their own innate belief. They also believe, you know, to keep their own current belief to some degree, or they also accept peer influence. And they might actually listen to the belief of others and what the others are telling them, and they might be actually influenced by the others. And what's really what's interesting now is that this simple model fits agentic, you know, dynamics, deliberation dynamics really well, you know, consisting of LLMs. And we can study now, you know, the different stubbornness levels, to which degree they accept influence, to which degree they trust. And what you can see is that works, oh, this is not very weird. Okay, so what you could see here is that this works across different kind of LLM model classes. It fits really well. And we also have, you know, that attacker, and we can even design attackers now that, you know, that work in the setting. Because we have now, you know, this is an analytically, theoretically tractable setting now, surprisingly. And in this one, we can also provide now guarantees for the interaction, but we can gain basic insights into how vulnerable the system is, for instance, also to stubborn agents that want to basically take over the whole system and project their opinion on others. And the key takeaway is from this relatively simple analysis, these are linear models in the end, is that a single stubborn agent is sufficient to completely hijack the consensus of its connected components, the agents essentially that are its connected components. So basically everyone that is somehow connected in this graph to this agent is vulnerable to the very stubborn agent. So only as long as someone is just very stubborn and insists on their opinion, they can basically dominate the whole process. If the others are willing to listen to them. Yeah, I see many ways nodding because that is also fits well in. So by the way, that was first developed in social sciences to model the interaction of people. And we can of course also study more different kind of topologies, like for instance fully connected networks or stars, and different kind of attack scenarios. So it's also really important where the agent is in this graph. So this attacker is, and we can then predict. And we can even write down the equations. We can write down in a closed form solutions, how the opinion of the whole system looks like after they deliberated. And and the key takeaway is basically if we can protect agents to some degree if we just increase their stubbornness. So as long as they're not willing to listen to others, of course, they cannot be easily be taken over by someone else. But of course, that's also not great, if they actually want to come to a consensus. Otherwise, if they actually want to solve a problem jointly. And in this context, we can then also study if there are other kind of ways to potentially make this system more robust to this adversarial takeover. And what you can see is that larger systems tend to be less vulnerable because there are kind of more people that kind of have an influence on the opinion formation process. We have also safe regions that you could potentially see because the left region here is green and the other one is kind of orange. So in this green region, everything is okay, essentially, so an adversarial agent cannot take over, but also because now the stubbornness of the others is sufficiently high. And, this problem is that all of this potentially can harm consensus or is very expensive if you want to have large systems. And also if you want to have large system, that only gives you a little bit of capacity. Okay, that's unfortunate. But we can at least also say something about how the graph topology is influencing that. So what you can see here is, of course, attacking the center of a star is really bad because you can reach everyone. That is more vulnerable than a fully connected network where a single agent is attacked. But that is still more vulnerable, the scenario, than if we attack a leaf of a star. So taking a leaf of a star is a bit more difficult because it can reach the others only via the center on this hop. And we can, of course, now study, how, basically can also show in experiments that our theory really holds, and, we find exactly that happening also in practice. And, and we have now multiple ways to increase the robustness, as I said, right? We can control the trust, potentially, in others, so whether others are willing to listen to this adversary, can control the behavioral traits, and we, so like how stubborn they are, and we can control the network size. But all of them have downsides. So either, this is very expensive, right, and still requires high stubbornness level, or we have also just higher stubbornness means we have less utility overall over the system because we can't really find, good consensus. So it means like everyone is less willing to collaborate. And that is usually not a good thing if you want the system to collaborate, and the utility of the system comes exactly from that collaboration. So what we do then, of course, try to do is find network effects. So adjust the network and the trust dynamics in such a way that ideally the agents do understand who is the adversary and can reduce then their trust only in that adversary, but are still willing to collaborate with everyone else. Of course, that is also error-prone potentially because we need to know who the adversary is, and we can, of course, devise adaptive defenses that try exactly to do this and that work to some degree, but this is then exactly the challenge. And that is what we found. What I found most striking is, that finally these kind of different things I've worked on come together, in this kind of setting where we can now study multiple agents in a graph, that interact with each other. We can care about efficiency, and we can even model the cascade process or the opinion formation in these models and potential cascades in that system, even from a relatively simple modeling perspective, and gain high-level insights that help us to protect now these systems that will likely change dramatically how we work together. And with that, I hope to democratize AI overall, but I do think we need everyone in this so that we can all participate in AI where that is hopefully also distributed to some degree, where our agents can collaborate effectively together and where everyone is able to have an influence on how AI is built. And with this, come big thank you to my group who made all of that possible and are the major driving forces between what I've just shown here in the front and also here somewhere in between. Thank you all, for being with me and for having been with me on this exciting journey and for continuing also to trust in me, to accept some influence from my side, to collaborate effectively in this. And also with great joy, I hope. We have recently grown very much, so this is a photo from yesterday, and I also need to thank Yil's PhD student. She was there to take pictures from us. So thank you very much for helping us. And last but not least, of course, not last, but of course also big thanks and a big shout out to my collaborators. A lot of them are actually also at CISPA. So for instance, Lea and also Mirela, will soon be, right? And, there was also Alexander was here for some Krikamol. Jonas was also here at some point in CISPA. So there are many great people that I had the pleasure to meet and to work with. It was a big honor. And of course, my family and my parents who are here today, thank you. Nothing of that would have been possible without you, or actually it was all because of you. And I hope that's okay for you. And, it was like nothing would have been, this whole cascade, and this kind of waterfall that was filled, that is all due to you. Thank you. And also thank you for being here and supporting me here on this journey. And last but not least, of course, to all of you, big thank you for being on this crazy journey with me. And it's a big honor and joy to be also a part of your journey. And it was a very big pleasure, and I hope there's many more to come. Thank you all. And especially also here to my mentor, Andreas, who made this, exactly, sorry. Andreas, and also many people, that helped me in the process and that, that also helped me, getting this ERC grant, all these fantastic colleagues. It would have by far not as much fun, without you, and also not possible, honestly, with you. I found that coming to CISPA was great. I was very amazed by this great atmosphere that we had here and this great support also that I got right from the start here, and everyone cared about, the others succeeding. So thank you. It was big. Thanks. Thank you.